On those thermo slides that you just received, they're not numbered. That's my bad. So if you take a look, you're going to be on the side that says Intro to Enthalpy. So make sure that's the side you're looking at. I know the writing's kind of small, but you're going to be writing most of the stuff in your spiral anyway. Intro to Enthalpy. But what the heck is thermo? Look here. I want you to take your hand. I want you to do this. Everybody, show me your hand. Come on. It's going to be fun. All right. Then what I want you to do is I want you to take that open hand and I want you to grab the leg of your chair or desk whole-handedly and don't let go. Grab it. Don't let go. You got it. Keep holding on. What was the first thing that you thought when you grabbed it? You probably thought cold. Why? What do you think made your nerves think cold? I don't like that answer. She said because the bar is colder than our body temperature. Keep holding it. In a nutshell, I would say that your body picked up on cold just because there's a difference in temperature between your hand and the bar. Any difference in temperature is going to make your nerves pick up on the fact that there's something different there. How's it feel now? You could probably still feel sensation, but is it as cold as it was 20 seconds ago? Let it go. Now, can anyone try to verbalize why the bar stopped feeling as cold as it did initially? All right. She said your body temperature is just producing heat, and she's saying that it's going to start to feel warmer if your body's moving heat towards it. What did you want to add?
This is related to the topic, but basically we don't have like weight sensors, so whenever you feel like water, it's only because it's like colder or hotter than like your actual weight. That's why if you put like your comforter in the dryer, you can never tell if it's wet or if it's just hot, you know what I mean? So you have to like let it lay out for a couple.
You're definitely the first one to bring up that phenomenon. Now, if I were to ask my initial question to a group of second graders, which, you know, it's fifth period, but anyways, y'all are good. If I were to ask the same question about the hand in the bar, there would probably be some of the students in the room that would have an opposite perspective. They might say, well, the cold from the bar is moving into your hand. All right, that's why you felt cold, and that's why initially it's going to start getting warmer because all the cold is leaving the bar and going into the hand, which is absolutely wrong. But there is a perspective issue there where you could see why someone might try to argue that. I'd like to let you know that the reason that that's blatantly wrong is that there's no such thing as cold. It doesn't exist. So when you have kids, don't teach them that it's cold outside, all right? And tell them to never wear a jacket. That's good parenting. No, the reason that there's no such thing as cold is because all of our instruments, I mean, everything scientific, has the ability to measure the presence of energy. Energy's most common form is heat. So we can either measure that there's a lot of heat in something making it hot, or not a lot of heat, in which case we see that as cold, even though that's not what's being measured. Thermochemistry takes a look at the phenomenon of heat transfer between items. In chemistry, we have to really focus on it being reactions, or we'll call them systems, because if we just say we're studying heat, well, that kind of becomes physics. All right, so we are going to apply the movement of heat to reactions. So a couple things that we need to cover in order to do this properly. If you look at your first slide there, enthalpy is what we'll study today and tomorrow, since this is a very abbreviated Thermochem study. But if you leave with nothing else, then leave with enthalpy. But the vocab word of enthalpy is simply the fancy way that we say we're studying the movement of energy, heat, for our sakes. Now, The change in energy is represented by a symbol. Does anybody know what symbol represents change? Yeah, triangle's correct. What's that called? Yeah, it's delta. So enthalpy is kind of defined as delta H, the change in heat energy. So today and tomorrow, we'll be looking at different ways to analyze delta H, how much the heat is changing in a system. But not only do we care about how much the energy is going to change, like when you grabbed your desk, we could calculate a number. This is usually a number of how many kilojoules of energy went in or went out of your hand. Kilojoules is going to be your new unit of delta H. But instead of just knowing what enthalpy is, there's secondary words to let us know whether the heat is going into the system, into the reaction, or leaving it. And these are words that you've probably heard of. All right. One of them, this is on your next slide, is endothermic. The other is exothermic. The prefixes of those words will certainly help you with their meaning, because remember, we're tracking the direction of delta H, which for endo, I'm going to say that heat is entering the reaction. So what do you think exothermic is? Yeah, we'll say heat is leaving the system. But since delta H, the actual measure of enthalpy, is going to be a number, there's another definitional part of these two words that's very important that you know. If a reaction is endothermic and the energy is traveling into the system, then the value that you get for delta H is going to be positive. So of course, if energy is leaving the reaction, then delta H is going to be negative. I want to mention on your slides that on the one before these words were covered, it mentioned the law of conservation of energy. So while these 2 days are going to be us tracking energy moving in and out of systems or reactions, I do want to mention that the amount of energy we have available in the universe is constant. There's no creation or destruction of energy, just transfers of its form. Where do we get all of our energy here on planet Earth, though? What's our source? The sun, right? All of the energy that we use comes from the sun. The autotrophs catch it, and we eat those autotrophs to harvest it. There's a couple ways that I need you to be able to analyze a reaction based on whether it's endo or exothermic. One of the ways is graphical. If we're graphing heat movement, here's what the graph will look like. It'll be an XY axis. The y-axis is going to be based on energy, while the x-axis will be based on time. So here's an example of how we can analyze one of these. Let's say that in a given system, the reactants were plotted there, while the products were plotted there. Those are reactants and products. So look at what's happening. As we go this direction, time is passing. And if you go this direction, the amount of energy present is increasing. So if you track this change over time, do you think I have graphed an endo or exothermic reaction here? Good guess. Yeah, I would say this is an endothermic reaction. Why? Well, I mean, look what energy did. As the reaction progressed, the amount of energy available increased. Therefore, we would assume that energy is being put into the system. Now, so you have it in your notes. I just want you to have an exothermic example. Of course, you could probably guess what this is going to look like, but energy versus time, of course, it would be any scenario where the products have less energy than the reactants, indicating that there has now been a loss of energy.
So is heat just energy?
Yep, heat's the most common form of energy.
So why do some people produce more heat than others?
So, I mean, in general, for us, our body temperature should be sitting at the 98.6. So that's our homeostasis. But if you have an individual that is like naturally producing more heat, meaning that maybe they sweat more often or whatever, that's physiological. So that's going to go against what our general study is here in regards to why that might be. So I don't have a better answer than that. So this is one of our endo-exo analyses. However, a more common one outside of these graphs is going to be looking at given situations. If I give you a real life situation, I say, hey, this happened. Do you think that was an exo or endothermic phenomenon? That you can figure it out. Now, to try to simplify this, because it's inherently confusing, as you'll see in a moment. By the way, let's get Aspen out there because we really want y'all to focus on this next part and be on your toes. One of the ways I can try to simplify this is by equating it to phase changes. Look up here at my arrows. Sorry, I'll get my screen out of your way. If you're on the video, pause it a second because I'm going to take you away quick. But what do you think SLG stands for? Yep, solid, liquid, gas. So if you equate the changes in the scenario to the arrows I've drawn, it can help unconfuse you if you get your brain mixed up. If you look at the third slide, you'll see a list of 7 examples. We'll do the first 3 together, and the next 4 we'll draw cards. So let me show you how we can think through this both rationally and using my cheat up there. Example 1, reading from your slide, says water freezes. Water freezes. So the question is, where's the heat going when that happens? All right. Well, do you think for water to freeze that we need to put heat into the water or take heat out of the water? Out of the water is the way to rationalize it. And some of y'all can just do that and you'll be really good at this. Or you might get confused. So if we use the guide up there, well, that means that the liquid water, of course, is turning into solid ice, exothermic according to the arrows. The other way this can become confusing has to do with the next 2 examples, because there's a perspective issue you can have when looking at endo-exo, because it turns out there's usually 2 things involved. Like if you go back to grabbing your desk, You could judge the exo-endo from the perspective of your hand or the perspective of the desk, and they'll have opposite perspectives. Look at this next example. I'll show you what I mean. Number 2, your hand gets cold when you touch ice. Your hand is getting cold when you touch ice. Do you think, now in this case, the subject is your hand, the system. Do you think that your hand is experiencing an exo or endothermic phenomenon in this case? Exo, right? Because if your hand is experiencing cold, that means the heat is leaving. But look at the third example. Ice gets warmer when you touch it. Now our system is the ice. Well, if the ice is getting warmer, I mean, most of y'all know what happens if ice gets warm. What's it do? It melts, in which case, what's the answer now? Endothermic. So you have to tread lightly so that you don't get confused. Let's draw some cards. Example number 4 says, water boils in a kettle. Water boils in a kettle. Let's go to cluster 2, seat 5. 2-5, what you think? This guess is endo. Do you agree or disagree? Agree, right? Boiling is a liquid turning into a gas, so that can help with the cheat if you can't see it rationally. Next one, water vapor condenses on a pipe. Water vapor condenses on a pipe. Let's go over to cluster 2 again. Seat 2. 2-2, what you think? His guess is exo. Agree or disagree? Also agree. Any questions? This is easy. Ice cream melts and we all cry about it. Let's go over to cluster 1. Seat 4. 1-4, ice cream melts. What you think? Endothermic's correct. And then finally, water drops evaporate off your skin after you exit the pool. Back to cluster 2. That's pretty wicked. Cluster 2, seat 2. That's just, I mean, I'm out of 2s now. The last one, water drops evaporate off your skin. Perfect. Endo. If you would, copy down the orange equation with the pink number before I continue. We're going to change gears to the other part of today. Copy down the orange equation and the pink number only. Yes? I'm going to go over it. But yes, the answer is yes, but I'm about to do them both in detail. There's 3 other ways I need you to be able to analyze Thermochem. We're going to do 2 of them tomorrow. But the other one today is one that's going to make you give me a mean face. But there's Thermochem stoichiometry. So let's talk about what that means. Now, we know that the study of stoichiometry is really simple. All right, it was just the comparison between quantities of reactants producing quantities of products. How much of this do you need to make this much of this? All right. By the way, those of y'all at home, these equations are the equations from the slides, if you didn't know that either. All right, I'm on that bottom slide right there. All right, so if you have this, it's right here. So you just copy down that equation. So my equations will be from the handout. Anyway, so looking at this orange equation, though, I want to explain what I see in regards to enthalpy. Do you see how the pink number says that it produces 2,221 kilojoules? Hey, is it exo or endothermic? It's negative, which makes it exothermic, right? Look back at your notes. Negative is exothermic. So what do these two numbers have in common? I haven't told you to write the green one yet. Don't. But no, both of the reactions are exothermic. I know that right away because the enthalpy change is negative. Let's talk about that for a moment. Before we get into the stoichiometry, the negatives and the positives in thermo are different than negatives and positives the way that you think of them. Like if I said you're negative $50, you immediately equate that as, well, that's bad. That means I owe someone 50 bucks, all right? But if I say I'm negative 2,000 kilojoules, the negative sign is different. Here's why. When studying Thermochem, there is an amount of energy that's either going to go in or out, and that's what we care about. The number is the amount of energy. So imagine that I had a positive 100 kilojoules and a negative 100 kilojoules. What they have in common is they're the exact same number. It's both 100 kilojoules of energy. The only difference between positive 100 kilojoules and negative 100 kilojoules here is which direction that 100 kilojoules is moving. So one's not more than the other. The positive 100 kilojoules isn't more than the negative 100 kilojoules. It's just the negative is going to be taken out of a reaction and then used for something else somewhere else, while the positive is going to go into the reaction to probably help drive it forward. So the positives and negatives that you run into are really, really important because it tells us what direction they're moving, but it's not changing the quantity of the number. The number is just how much energy you have, positive or negative. If I look at this orange reaction, here's what I see thermochem-wise. I see that if I'm going to produce this much energy, if that much energy is going to be given off, negative exothermic. Every time I have 1 propane, 5 oxygens, 3 carbon dioxides, and 4 waters, every time I have 1 and 5 of those producing 3 and 4 of those, it's going to give off that much energy. This delta H it's giving you, it's 1 click of the reaction. So what if I had 2 of those and 10 of those? Well, it would produce 6 of those and 8 of those. What do you think would happen to the delta H if the reaction clicked twice? It would be, right, that was really specific, but yeah, it would be twice as much, all right? So again, the enthalpy that you're given for a reaction tells you how much energy is given off or taken in if it's positive when the reaction happens one time. And for this reaction to happen one time, it's a 1-to-5 ratio, produces 3 to 4. All right, so we'll want to have that in mind. If you look at the slide that I'm referring to, it gives you a starting amount of one of the reactants. It says, what if you had 5 grams of the propane? All right, we're assuming the other one's in excess, so we're assuming he'll be the limiting reactant, and he's going to determine everything. It wants to know, okay, well, what will the delta H be if you have 5 grams? Well, here's what I know. I know that if 5 grams is equal to 1 mole, then that will be the number, right? Because if you have 1 mole of this, that pink number is what's produced. But I'm not sure off the top of my head how many moles 5 grams is, which is why this becomes stoichiometric. So work along with me. Let's check it out. I'm starting with 5 grams of propane. So we're going to have 5 grams of propane. Now, if you remember nothing from stoichiometry, please know the red line there. All right? Remember the red line. No matter what, the item that we start with our analysis with must be in moles. All right, so we're going to get back to our conversions here. It's not starting us in moles. So I don't want grams of C3H8. I want moles of it. Now, here's the newest part. Here's the newest part today. Look here. Once you have moles of the item you're analyzing, you can convert directly to kilojoules. That's brand new information. I'm going to show you how to do it. But what I just said is once I have moles of the item we're looking at, you can convert that directly into kilojoules. I'm going to bring down my diagonals to move forward. All right, let's see what we remember here. Hey, look, moles is over grams. What's the conversion factor for moles when that happens? It's 1 over periodic table. All right, that was pretty impressive. Good job. Now, I already have this number, but you would get out your periodic table. You'd go look at the molar mass of 3 carbons and 8 hydrogens. I get 44.1. Back to the new parts, though. Look here. You've not seen this before. The kilojoules over moles is related to the given delta H, given enthalpy. But the mole of that pink number is related to the coefficients. All right? So in other words, these two values for the conversion factor, one of them comes from the given enthalpy, in this case, negative 2221. And the mole value is the coefficient of the item you're looking at, which is what in this case? It's 1. Now, I hate it when moles is 1 and it's not always 1 because y'all get confused, all right? What would that square have been if we were analyzing oxygen? It would have been 5. So realize the way I thought through that there. Multiply across the top, divide by the product of the bottom. So let me ask you this, looking at that number, did we react less than a mole of propane or more than a mole of propane? Definitely less, right? Because we knew right off the bat that if we react 1 mole of propane, it produces over 2,000 kilojoules. Well, how much did 5 grams produce? Just over 200 kilojoules. So we were way under a whole mole. Let's do another one. Copy down the green reaction now. It's the next slide in your notes. They're not original problems. Copy down the green reaction. Remember what I see thermochem-wise. Every time 4 sodiums reacts with 1 oxygen and produces 2 sodium oxides, it will give off negative again, otherwise I would say take in. It will give off 828 kilojoules of energy. All right? The question, if you look to the slide, says, okay, well, how much energy is given off if you produce 1 mole of the sodium oxide? Now, some of you might be able to look at these nice whole numbers. They're not usually not so pretty like this, but this is a really nice whole number. You might be able to figure out the answer without stoichiometry. We're going to go through the steps, but I'll show you what I mean at the end, but kudos if you can see it already. But I'm going to take the given, which is 1 mole of sodium oxide. Do you see good news or bad news here? Yeah, anytime moles is given, it's always helpful. I already have moles of the item in question, so for Thermochem, I can now convert directly to kilojoules, just like last time. Bring down the diagonal. When kilojoules is over moles, I can use my known enthalpy of the reaction connected to the coefficients of the reaction. So my kilojoule value here will be the negative 828. And what will the bottom number be? 2. The reason I think that the whole numbers could have allowed you to rationalize this without doing all the work is that, remember, the work says that if you produce 2 of those, it makes that much energy. And then it asked, well, what if you produce just 1 of them? All right, well, that's half of the reaction. Therefore, it's half of the energy. But again, you don't usually get those pretty numbers. Yeah. You don't. I mean, no, for sure not, right? Like, for those of y'all that take AP next year, anytime you can save time, oh my God, save time, all right? But like I said, this would probably more likely be something like 1.75 moles, in which case it's a little murkier. All right, let's look at one more problem, but we're not going to do any math on it. I want you to look at the next slide. The last one for today is on the back. We're going to draw a card right off the bat. I know it's kind of small, but if you squint, it's the one that has the decomposition of 6 iron 2 oxides. And I want to go ask a question to cluster 6. Uh-oh, Aspen, it's you and me. Hey, Aspen, here's my question. If you look closely, it gives you an enthalpy. I want to know, is that reaction exo or endothermic? We are on, it's the one, I'm right here. I'm in the top corner on the back. And then it's got an enthalpy there near the top right of the slide. Exo or endo? She says endo. Agree or disagree? What? Is it positive or negative? Positive. Endothermic. She's right. Go ahead and pass Aspen. Good job. Yeah. The given enthalpy is positive, and positive is endo. Now, here's the next thing I want you to do. Focus. We're almost done. There's another reaction on the slide. I want you to compare them. They have something in common. How do the 2 reactions compare to each other? They're reversed. One's going the other way. All they're doing, look here, is reversing the arrow. Here's what I want you to know about Thermochem. You see this orange equation? If I were to reverse the arrow, the same amount of energy would move. But what would be the difference? It would move the other direction. So what do you think happens to the enthalpy value if I reverse the arrow? It just flips the sign. Same amount of energy. So if I reverse the orange sign, positive 2221. If I reverse the green symbol, positive 828. It would turn from exo to endothermic. So what then is the answer to the question on the slide? What is the enthalpy change for the bottom reaction. Negative 472 instead of the positive for the forward.